Hello, welcome to the video lecture series on digital image processing. In today's class, we will continue with our discussion on image segmentation. In the last class, what we have seen is we have discussed about the image analysis. We have seen what is image analysis and the role of image segmentation in image analysis process. We have seen that there are mainly two approaches for image segmentation. The first approach is discontinuity based image segmentation technique and the second approach is region based image segmentation technique. What we are discussing now is the discontinuity based image segmentation technique. Then we have seen that to implement discontinuity based image segmentation technique, first what we have to do is we have to detect the edges present in the image. Edges means it is a region where there is a variation either from the low intensity value to a high intensity value or from a high intensity value to a low intensity value. So, in such transition regions, we have to detect the position of an edge and by this what is expected is to get the boundary of a particular segment. But the problem we have discussed in this process that because of the problem of illumination, if the illumination is non-uniform or if the image is noisy, in that case the boundary points or the edge points that we get after the edge detection operation, those points are not continuous. So, to take care of this problem, what we have to do is after we detect the edge points, we have to link the edge points. So, we have said that there are two approaches for linking the edge points. The first approach that we have discussed in the last class is the local processing approach and the second approach that we will be discussing today, that is a global processing approach, which is also called Hoff transformation. So, after today's lecture, the students will be able to explain and implement the local processing technique for linking the edge points and also the global processing technique, that is the students will be implement the Hoff transformation to link the edge points. So, let us just see that what we have seen in the last class. We have said that ideally edge detection technique should identify the pixels lying on the boundary between the regions. We say it is the boundary between the regions because we assume that it is a transition, this region is a transition region from a low intensity values from low intensity region to a high intensity region or from a high intensity region to a low intensity region. But while trying to implement this, it has been found that the edge points which we expect to be continuous to give us a meaningful boundary description of a segment, that cannot be achieved in practice. Now, this is mainly due to two reasons. First one is due to non-uniform illumination of the scene. If the scene is not uniformly illuminated, that leads to detection of edge points where the boundary points will not be continuous. And the second reason for getting this non-continuous boundary points is the presence of noise. That is, if the image is noisy, then after doing the edge detection operation, either the boundary points will not be continuous or there may be some spurious edge points which are not actually edge points or the boundary points of any of the regions. So, to tackle this problem, we have to go for linking of the edge points, so that after linking we get a meaningful description of the boundary of a particular segment. So, we have said that there are mainly two approaches for edge linking operation. The first approach is the local processing approach, and the second approach is the global processing approach. In the local processing approach, what we do is we take an edge detected image, that is the image that we have as an input. This is an image containing only the edge pixels. So, we assume that edge points will be white and all the non-edge points will be black. And in this edge detected image, we analyze each pixel in a small neighborhood. So, for every point x y, if that is an edge pixel, we take a small neighborhood of point x y and we link the other edge points within this neighborhood with the point x y if they are similar in nature. So, whenever we find that within the neighborhood we have two edge points which are similar in nature, then we link these edge points, and after linking all such edge points we get a boundary of pixels that are similar in nature. So, basically what we get is a well defined boundary of a particular segment. So, when we say that we have to link the edge points which are similar in nature, then we have to have some similarity measure. So, remember that after edge detection operation, for every edge point we get two quantities. One is the boundary strength at that particular edge point, and the second quantity, that is the direction of edge at that particular edge point. So, by comparing the boundary strength as well as the direction of a boundary at point x y and at a point which is in the neighborhood of x y, we try to find out whether these two points are similar or not. So, if these 2 points are similar, we simply link them. So, for this what you have to do is we take an edge point x y and we find out a point x dash y dash which is in the neighborhood of x y. So, what we are doing is we are taking this point x y and considering the point x dash y dash which is in the neighborhood of x y, and we find out the difference of edge strength. We know that this gradient operator f x y is the image function, and f x y gives the intensity value at location x y in the image, and grad f x y, this gives you the gradient of the intensity value at location x y. So, we compute the gradient of at location x y and also the gradient at location x dash y dash, and if the difference between these two is less than or equal to certain threshold t, where t is a non-negative threshold, and at the same time, so this gives you whether the strength is similar or not, and at the same time we also have to check whether the direction at this edge which is given by this alpha x y at location x y and alpha x dash at location x dash y dash. So, if the orientation or the direction of the edge is also similar, that is the difference is less than or equal to some angle threshold value a, then we consider these 2 points x y and x dash y dash to be linked together. So, in this particular case our x dash y dash has to be in the neighborhood of x y. So, that is what is represented by x dash y dash belongs to neighborhood of x y. So, this is the local processing technique. but as we said that we are going for linking of the edge points because the edge points are discontinuous, and normally the neighborhood size that is taken is a small neighborhood. So, if x dash y dash is not within the neighborhood of x y over a given definition of the neighborhood, in that case x dash y dash cannot be linked with the edge point x y. So, to solve this problem, because x dash y dash, the two edge points can be far apart depending upon the amount of noise that you have or the depending upon the lighting condition, but we have to be we should be able to link those points as well. So, in such cases the local processing technique does not help to link the edge points. What we have to go for is the global processing technique, and the global processing technique that we will discuss today is called the Hopf transformation. So, it is Hopf transform. So, what is this Hopf transform? The Hopf transform is a mapping from the spatial domain to a parameter space. So, let us take an example. Suppose I have this x y coordinate system and I have a single state line in this x y coordinate system. And we know that in the slope intercept form, this straight line is described by a equation which is given by y is equal to m x plus c, where m is the slope of the straight line and c is the intercept value. Now, for a particular straight line, the values of m and c will be constant. So, I represent them by m 1 c 1, indicating that these two values, the slope and the intercept, are constant for a particular given straight line in the x y plane. So, you find that this particular straight line is now defined, is now specified by two parameters. One of the parameters is m 1, which is the slope of the straight line, and the other parameter is c 1, which is the intercept. Now, if I map this straight line to the parameter space, because I have two parameters m and c, that is slope and intercept. So, our parameter space will also be a two dimensional space. So, what I am trying to do is, I am trying to map this straight line in the parameter space. So, I draw this MC plane. I will have the slope m along one direction and the intercept c along another direction. And since for this given straight line y equal to m 1 x plus c 1, m 1 that is the slope and c 1 that is the intercept is fixed. So, this particular straight line will be represented by a single point in the MC plane, and this point is at location m 1 and c 1. So, you find that when I map a given straight line in the spatial domain to the parameter space, a straight line gets mapped to a single point. Now, let us see what happens if we are given a point in the spatial domain, that is in the x y plane we are given a particular point. Let us see the situation. What will happen in this case? So, now what I have is, I have again this x y plane, and in the x y plane I have a single point, and let us assume the coordinate of this point is x 1 y 1. Now, find that equation of any straight line in the x y plane, as we have seen earlier in the slope intercept form, is given by y is equal to m x plus c. Now, if this straight line y is equal to m x plus c has to pass through this given point x 1 y 1, then x 1 y 1 must satisfy this equation. So, in effect, what I will get is, I will get an equation that is y 1 is equal to m x 1 plus c, because this line y is equal to m x plus c is passing through the given point x 1 y 1, and this is the equation that has to be satisfied by all the straight lines that passes through this point x 1 y 1. Now, find that ideally I can have infinite number of straight lines passing through this given point x 1 y 1. So, there will be infinite number of straight lines like this, and for each of these straight lines the value of the slope, that is m, and the intercept c, it will be different. So, if I now map this single straight line in our parameter space, that is M C plane, you find that this m and c, these two become the variable, whereas y 1 and x 1, they are the constants. So, now what I can do is, I can rewrite this equation, that is y 1 equal to m x 1 plus c, in this way. I can write it as c is equal to minus m x 1 plus y 1. So, here what I have is, I have this x 1 and y 1, these two are constants, and c and m are variable. So, if I map this point x 1 y 1 into our parameter space, so what I will have now is, I will have this M C plane, and in the M C plane you find that c equal to minus m x 1 plus y 1. This is now the equation of a straight line. So, effectively what I get is, I get a straight line in the M C plane following the equation c is equal to minus m x 1 plus y 1. So, we have seen two cases, that in one case a straight line in the x y plane is mapped to a point in the M C plane, and in the other case, if we have a point in the x y plane that is mapped to a straight line in the M C plane. And this is the basis of the Hopf transformation, by using which we can link the different edge points which are present in the image domain, which is nothing but the spatial domain, or we can say that this is nothing but our x y plane. So, now let us see that what happens if I have 2 points in our spatial domain or the x y plane. So, again I go to our spatial domain or x y plane. So, this is my x axis and this is my y axis, and suppose I have 2 points, one is say x I, y I, and the other point I have in this spatial domain is x j and y j. Now, if I draw a straight line passing through these points x I, y I and x j, y j, say this is the straight line which passes through these 2 points x I y I and x j y j. And we know that this straight line will have an equation of the form y equal to say m dash x plus c dash. So, what we have to do by using the Hopf transformation is that given these 2 points x I y I and x j y j, we have to find out the parameters or the equation of the straight line which is passing through these 2 points x I y I and x j y j. Now, as we have seen earlier that a point in the x y plane is mapped to a straight line in the MC plane or in the parameter space. So, here in this case, since we have 2 points in the x y plane, this will be mapped to 2 different straight lines in the MC plane. So, if I draw in the MC plane, if I find the mapping in the MC plane, it will be something like this. So, I have this parameter space or MC plane. The first straight line, the first point x I y I will be mapped to a straight line like this, where the equation of this straight line will be given by c equal to minus m x I plus y I. And the second point will be mapped to another straight line, say something like this, where the equation of this straight line will be given by c equal to minus m x j plus y j. And you find that the point at which these 2 straight lines meet, that is this particular point, this is the one which gives me the values of m and c. So, this will give me the value of m dash and c dash, and this m dash and c dash are nothing but the parameters of the straight line in the x y plane, which passes through these 2 given points x I y I and x j y j. Now, if I consider that there are infinite number of points, or there are a large number of points lying on the same straight line in the x y plane, each of these points will be mapped to a particular straight line in the MC plane like this, but each of these straight lines will pass through this single point m dash c dash in the parameter space. So, by this what we have seen is, as we know that if there is a single point in the parameter in the spatial domain or in the x y plane that is mapped to a single straight line in the parameter space, that is MC plane. So, if I have a set of collinear points in the x y plane, each of these collinear points will be mapped to a single straight line in the parameter space or in the MC plane. But all these straight lines corresponding to the points which are collinear in the x y plane will pass through, will intersect at a single point, and this point in this case is m dash c dash, which value, the values of which, that is m dash and c dash, this give us the slope and intercept values of the straight line on which all those collinear points in the spatial domain lie. And this is the basic essence of using Hopf transformation for linking the edge points. Now, how do you compute this Hopf transformation? So far what we have discussed, this is in the continuous domain, that is our assumption is the values of m and c, or m and c are continuous variables. But in our implementation, since we are considering the digital cases, we cannot have the continuous values of m and c. So, we have to see that how this Hopf transformation can really be implemented. So, for implementation, what we have to do is this entire MC space has to be subdivided into a number of accumulator cells. So, as has been shown in this particular figure. So, here you find that what we have done is this MC space, MC plane is divided into a number of smaller accumulator cells. So, here we have a range of the slopes which are the expected range of slopes in a particular application, and the range is from m minimum, that is the minimum slope, to a maximum slope. So, this is the minimum slope value m minimum, and this is the maximum slope value m maximum. Similarly, for C, this is also subdivided and the total range is within a expected maximum value and a minimum value. So, C minimum is the expected minimum value of the intercept C, and C maximum is the expected maximum value of the intercept C. So, within this minimum and maximum, within this range, this space is divided into a number of accumulator cells. And this array, this two dimensional array, let us name this as an array, say A. And each of these accumulator cell locations can be indexed by, say, index I and j. So, a cell location at location, say, I j, I may call this location as a cell location I j, and the corresponding accumulator cell will have a value, say, A I j. So, this A I j, this particular cell, the I jth cell corresponds to the parameter values, let us say m I and C j. So, an I jth, an accumulator cell I j having an accumulator value A I j corresponds to the corresponding parameter values m I and C j. And for implementation, what we do is we initialize each of these accumulators to 0. So, initially A I j is set to 0, and that is our initialization. Okay. So, once we have this array of accumulator cells, then what we do? In the spatial domain, we have a set of boundary points, and in the parameter space, we have a two dimensional array of accumulator cells. So, what we have to do is, we have to take a boundary point, say x k, y k, a single boundary point in the spatial domain, and we have seen earlier that this boundary point x k y k is mapped to a straight line in the parameter space, that is in the M C plane, and the equation of this straight line is given by C is equal to minus m x k plus y k. Okay. So, what we have to do is, we have to find out the values of m and c from this particular equation. Now, in our case, what we have is the values of m and c are not continuous, but they are discrete, and as we have said that an ijth accumulator cell corresponds to the corresponding parameter values m, I and c j. So, to solve for values of m and c, our basic equation is c equal to minus m x k plus y k. So, here what we do is we allow the value of m to vary from the minimum to the maximum, as we have said that we have chosen a range m minimum to m maximum. So, we allow the value of m to take all possible values or all allowed values as specified in our accumulator cell, ranging from the m minimum to m maximum. And for each of these values of m, we solve for the corresponding value of c. Following this particular equation, c is equal to minus m x k plus y k. Now, the value of c that you get by solving this particular equation for a specific value of m, that may be a real number, whereas we have to deal with the discrete case. So, whenever we get a value which may be a real number or maybe the value of c that we get which is not allowed as per our definition of the accumulator cell, then what you have to do is this value of c has to be rounded off to the nearest allowed value of c as specified in the accumulator cell. So, if I have say n number of such possible values of m, I will get the n number of corresponding values of c by solving this equation c equal to minus m x k plus y k. So, suppose by following this, a particular choice of m, say m k, or we have already used k for something else, instead of calling it m k, let us call it say particular value of m, say m p. When I put this value of m p, this m p in this equation, suppose the corresponding value of c I get after solving this equation is say c q. And you remember that we have initialized our accumulator cells to all the cells having a value of 0. So, whenever for a particular value of m p, I get a value of c q, that is the intercept value, then the operation I do is the corresponding accumulator cell a p q is incremented by 1. So, I make a p q is equal to a p q plus 1. So, this I have to do for all the points, all the boundary points in our spatial domain, that is in the x y plane, and for each of these boundary points I have to compute it for every possible or every allowed value of m as allowed in our parameter space. So, at the end you will find, because for every computed value or computed values m p c q, I am incrementing the accumulator cell by 1, where the accumulator cells are initialized to 0. So, you find that at the end of the process, if an accumulator cell a I j contains a value say capital Q. So, we are considering this after we consider all the boundary points in the spatial domain. For each of these we compute the corresponding say m p and c q. For all allowed values of m, I find out the corresponding allowed values of c, and for each such pair of m p and c q, I do this incrementation operation on the accumulator cell. So, at the end if an accumulator cell say Aij contains a value of say capital Q, this indicates that there are q number of points lying on a straight line whose equation is given by y is equal to m I x plus C j, because as we said that this accumulator cell I j corresponds to the slope value of m I and the intercept value of C j. And for every point wherever I get a corresponding value of m and c, the corresponding accumulator cell is incremented by 1. So, at the end of the process, if a particular accumulator cell A I j contains a value capital Q, this is an indication that in the spatial domain I have capital Q number of points or boundary points which are lying on the straight line y is equal to m I plus C j. Now, the question is what is the accuracy of this particular procedure, that is how accurate is this estimation of m I and C j. That depends upon how many number of accumulator cells I will have in the accumulator array. So, if I have a very large number of accumulator cells in the accumulator array, then the accuracy of the computed m and c will be quite high, whereas if I have small number of accumulators accumulator cells in our accumulator array, then the accuracy of these computed values will be quite less. Now, the question is how can we use this to detect the number of straight lines present in the spatial domain. Let us consider a case like this. Say I have an image in the spatial domain and the boundary points of this image are something like this. So, these are the boundary points in the straight line. So, when I compute this Hopf transformation, I get an accumulator cell. So, you find that in this particular straight line there are 1, 2, 3, 4, 5, 6, 7, 8 number of points on this side. On this straight line there are 1, 2, 3, 4, 5 number of points. On this part of the straight line there are again 5 number of points. On this part of the straight line there are 4 number of points, and if I consider that this part is also a straight line. So, on this straight line there are 3 number of points. So, in our accumulator cell at the end of this Hopf transformation operation, I will get one cell with value equal to 8, I will get another cell with value equal to 5, I will get one more cell with value equal to 5, I will get one cell with value equal to 4 and I get another cell with value equal to 3. And if I choose all these values, so if I say that I will consider a straight line to be significant if the corresponding accumulator cell contains a value greater than or equal to 3, then by this process the number of straight lines that I will be able to detect is this straight line, this straight line, then this straight line, this straight line as well as this straight line. But if I say that I will consider only those straight lines to be significant where the number of points, number of collinear points lying on the straight line is greater than or equal to 4, then I will be detecting only this straight line, this straight line, this straight line and this straight line. So, again here you find that by choosing that how many points to be I should consider to lie on a straight line, so that the straight line will be significant, and I consider this to be a boundary straight line, that also can be varied or tuned depending upon the application by choosing the threshold on this number of points lying on the state line. Now, here you find that in the MC plane, though we are able to find out the state line segments, but this particular formulation of Hopf transformation, that is mapping from xy domain to the parameter domain, that is the MC plane, has a serious problem. The problem is, in MC plane what we are trying to do is, we are trying to find out the slope intercept value of the state line in the spatial domain. Now, the problem comes when this state line tries to be vertical, that is parallel to x axis. If the state line is parallel to x axis, then the slope of the state line, that is the value of m, tends to be infinity. And in this formulation, we cannot tackle the value of m which becomes very large or which tends to become infinite. So, what should we do to solve this problem? So, to solve this problem, instead of considering the slope intercept form, what we can do is, we can make use of the normal representation of a state line. So, the normal representation of a state line is given by this. The formula is rho equal to x cosine theta plus y sin theta. And what do we get in case of this normal representation? The line that we get is something like this. So, here again I have this state line in the xy plane, but instead of taking the slope intercept form, where the equation was given by y is equal to m x plus c, I take the normal representation where the equation of the state line is given by rho is equal to x cosine theta plus y sin theta. What is rho? Rho is the length of the perpendicular. It is the length of the perpendicular dropped on the state line drawn from the origin of the xy plane, and theta is the angle made by this perpendicular with the x axis. So, you find that the parameters of the state line, which is defined in this normal form, rho is equal to x cosine theta plus y sin theta. The parameters are rho, which is the length of the perpendicular drawn from the origin to the given state line, and theta, which is the angle formed by this perpendicular with the x axis. So, unlike in the previous case where the parameters are the slope m and c, now my parameters become rho and theta. And when I have these two parameters rho and theta, then the situation is quite manageable. That is, I do not have the situation of leading to a parameter which can take an infinite value. So, you find that in this particular case, what can be the maximum value of rho and the maximum value of theta? We consider the value of theta to be ranging in the range of plus minus 90 degree, and the value of rho, that is the length of the perpendicular to the straight line from the origin, to be square root of m square plus n square, where m by n is the image size. And this is quite obvious, because if I have an image of dimensions say m by n, say here the image dimension is there are m number of rows and say n number of columns, and this is the origin of the image plane. And in this you can find that I cannot draw any straight line for which the value of theta will be beyond this range plus minus 90 degree, and the value of rho will go beyond this plus minus, this should be plus minus square root of m square plus n square. But what is the difference of our earlier formulation with this formulation? Now, in this particular case, our equation of the straight line is taken as rho equal to x cosine theta plus y sin theta. Whereas, in our earlier case, our equation was y is equal to m x plus c. So, here you find that in this particular case, given a single point say x 1 y 1 in the spatial domain, in the parameter domain, in the MC plane, the corresponding equation becomes c is equal to minus m x 1 plus y 1, which is again the equation of a straight line. So, when we consider the parameter space to be MC space, or we represent a straight line in the slope intercept form, in that case a point is mapped to a straight line in the parameter space. Whereas, in this particular case, for the same given point x 1 y 1, in the parameter space the equation that we get is rho is equal to x 1 cosine theta x 1 cosine theta plus y 1 sin theta. So, here you find that this x 1 and y 1, these two are constants for a given point x 1 y 1 in the parameter space, whereas the rho and theta they are variables. So, a particular point in the spatial domain is now mapped to a sinusoidal curve in the parameter domain or in the rho theta space. However, if I have q number of collinear points in the xy plane, which will be mapped to q number of straight lines in the MC plane, but all those straight lines will pass through a single point. In this case, the same q number of collinear points in the xy plane will be mapped to q number of sinusoidal curve in the rho theta plane, but all those sinusoidal curves will intersect at a particular point, at the single point, which gives us the values of rho and theta, which are the parameters for the straight line on which all those q number of collinear points lie. Now, this is the only difference between the MC plane and the rho theta plane. Apart from this, the formulation is exactly same as before. So, for computation, again here what we have to do is, we have to divide the rho theta space into a number of accumulator cells. So, the accumulator cells are given like this, as in this figure. So, here again any ijth accumulator cell, an accumulator cell say ij, this ijth accumulator cell, which will have an accumulator value of say aij, corresponds to our parameters theta I and row j. So, again as we have done in our previous formulation, that for a given point, as we have seen that our equation becomes rho is equal to x cosine theta plus y sin theta, and for a given point say x k y k in the spatial domain, our equation becomes rho is equal to x k cosine theta plus y k sin theta. What we do is we allow the value of this variable theta to assume any of these allowed values as given in this accumulator cell. So, the theta can assume any of these allowed values between this given maximum and minimum, and we solve for the corresponding value of the rho. And because the solution of rho that you get may not be one of the allowed values. So, what we have to do is we have to round off the value of rho to one of the nearest allowed values in our rho axis. So, again as before, that at the end of the process, if an accumulator cell say A I j contains a value equal to q, this means that there are q number of collinear points in the spatial domain, which in the spatial domain lying on the state line, which satisfy the equation rho j is equal to x cosine theta I plus y sin theta I. So, again as before, depending upon the number of points, putting a threshold on the number of points which we consider to be a significant point or not, I can determine how many state lines in the given boundary image I will extract, which will give me a meaningful boundary description. Now, let us see by applying this technique what kind of result we can get. Yeah, here what we have shown is, as we have said, that every point in the spatial domain is mapped to a sinusoidal curve in the parameter domain in the rho theta plane. So, you find that this point 1 over here has been mapped to a straight line, the point 2 has been mapped to a sinusoidal curve as has been given by this, the point 3 again has been mapped to this particular sinusoidal curve, 4 has been mapped to this particular sinusoidal curve, and 5 has been mapped to this particular sinusoidal curve. And now you find that if I want to find out the equation of the straight line passing through say 2, 3 and 4, these 3 points, then you find that 2, 3 and 4, these 3 sinusoidal curves are meeting at this particular point in the rho theta plane. So, the corresponding cell will have a value equal to 3, indicating that there are 3 points lying on the straight line which satisfy this particular value of theta and this particular value of rho. So, from here I can get the parameters of the straight line on which these 3 points 2, 3, 4 they are lying, and same is true for other cases as well. For example, 1, 3 and 5. So, you find that this is the curve for 1, this is the curve for 3 and this is the curve for 5, and all of them are meeting at this particular point. So, here whatever the value of theta and rho I get, that is the parameter of the straight line passing through these points 1, 3 and 5. So, by applying this, you find that in one of our previous classes we had shown this image. So, here we had shown that we have an image of a brick, and after edge detection operation what we get is the edge points as given on this right hand side. And now, if I apply the Hopf transformation and try to detect the four most significant state lines, then by applying Hopf transformation, I find these four state lines which are most significant. And the boundary which is specified by these four state lines. So, I can always find out that what are these vertex locations, and this is a rectangular region which is actually the boundary of this particular object region. So, with this we come to the end of our today's discussion, that is the global edge linking operation, where the global edge linking is done by using Hopf transformation, and as we have said that this Hopf transformation is nothing but a process of mapping from the spatial domain to the parameter space. And now, let us see some of the quiz questions on today's lecture. The first question is, what is Hopf transform? Second question, what determines the accuracy of Hopf transform? Third question, what is the difficulty of implementing Hopf transform using slope intercept representation of state line? Fourth, how is this problem solved using the normal representation of state line? And fifth question, is Hopf transform limited to detection of line segments only? Thank you.